Right, so in this session we're going to focus on and concentrate initially on the required practicals. So required practical 1 from paper 1 is the one from the acids topic. We did a full review of the acids topic, so I'm going to spend limited time on this, but it's really worth having another look at. So the idea of required practical 1 is it's a reaction, it's a neutralization reaction of an acid plus a base to give us salt and water. That's one of those general reactions of neutralization that you would know. But there are some details here. So the acid is always going to be one of the strong acids, probably going to be hydrochloric acid or sulfuric acid, but it could be nitric acid. If you don't know the formula of those acids, this is my reminder that you should know them. The base is an insoluble base when we do this experiment, and therefore it's going to be something that neutralizes the acid, which is the definition of a base, and it's insoluble, which means it's going to be a metal oxide or a metal carbonate. So it could be, if I write M, I mean metal, but it could be magnesium or zinc or calcium or copper or whatever. I'm going to use magnesium oxide, or it could be magnesium carbonate. So it could be any carbonate or any oxide. So acid plus base. Now the salt that you produce is a soluble salt, and that's what makes it, this practical, something of a challenge, that you can't just, you can't just mix two things together and produce this salt that you can have crystals of. You've got to do some stuff, and the details of that you need to know. And it's worth remembering that you generate water here in this reaction, and we need there to be no water when we've got the dry salt in the end. So, and also the fact that the acid and the alkali are dissolved in, or the acid, sorry, is dissolved in water. So there's lots of water that we have to kind of get rid of. The salt, you can work out the salt from the metal and the acid that you've got. And I know you know this stuff from just one tiny sec of the metal. I forgot what I was saying. What was I saying? Oh, the salt you can work out the formula of from the metal of the metal oxide or metal carbonate and the acid. So it'll be magnesium nitrate or magnesium sulfate or magnesium chloride. I would encourage you for the salt, the key thing to remember with the salt is make sure you work out the formula. Don't just guess the formula. Don't go, well, it's calcium chloride, so it's probably that. You've got to try to work out what the formula is. And for that, you'll need to know what the charge of the metal is and the charge of the non-metal. And you can work that out from the periodic table. You know how to do that. And if you don't know how to do that, look it up or ask over the next couple of days. And so you need 2 chlorides if it's a calcium chloride, or you'll need magnesium nitrate. You know nitrate is 1 minus hopefully, so you'll need 2 nitrates and 1 magnesium. If you're not sure how to do that, look up over the weekend how to work out the formula of ionic compounds. These are always ionic, by the way, compounds, and so you can think about that, and it might be that you do electrolysis of the products, who knows. Right, so what about the method then, which takes into account the fact that it's insoluble and that the salt is soluble? So to start with, we'll look at what we do with the oxide. If it's the oxide, you add the oxide to acid, but the acid has to be hot. So I'm going to simplify this as much as I can. Add oxide to hot acid. You heat it, and then you take the Bunsen away, otherwise it will boil, and that's dangerous. And if you heat sulfuric acid too much and you boil it, you generate some nasty gases. You get sulfur dioxide, which is nasty. So you heat it up, take the Bunsen away, and chuck in the oxide. But you do it a bit at a time. As you add it, it will react and it will disappear until you've added enough to use up all of the acid. So the key thing here, the detail we're adding here, is we add an excess of the base to use up all the acid. And we know we've used an excess because we've used up, because we start to see the powder not dissolving. We keep adding a little bit at a time until it stops dissolving. And the key thing there is that we've used up all acid. That means you've got an excess of the base in there, So we filter to remove metal oxide. The next stage is the same for both. So I'm going to move on to the carbonate now. So if you've got a metal carbonate, this is where it's different. So for the metal carbonate, add carbonate to cold or room temperature. Carbonates happen to react a lot more quickly, and you certainly don't want to heat them because it would be quite a violent reaction if you heat them up. And the key thing, of course, that you know is that carbonates, if you do this reaction, and I haven't added it here, so acid plus base goes to salt plus water. If it's a carbonate, you also get carbon dioxide. This is a chance to remind you that when you're writing a word equation, write words, and it will tell you this in the exam paper. And if you're writing a balanced equation, write the formulae. Okay? And there's a difference between those. The reason, by the way, we heat the acid with the oxide is this reaction is slow, and you know from the rates of reaction topic in paper 2 that if you heat it up, it will react faster. That's all it is. It's just so that it happens a bit quicker. The carbonate, because carbon dioxide is being produced, we'll see it fizzing. So if you're asked to say what the observations are, say what you see. So you'll see that, so that's an observation. And you keep adding until it stops fizzing. Add until stops fizzing. And then after that it's the same, so filter. And what you end up with then is the soluble salt dissolved in water. Now that's not what the exam board want you to produce. They want you to produce the salt. And so the way that you do that, there's a couple of ways of doing it, but the way that the exam board want you to write about, so make sure you use this method, is you heat that soluble salt in an evaporating basin over a hot water bath. So heat that, the water boils, can you see all of that? Yeah. Heats the evaporating basin. The water, probably half the water evaporates, you're then left with, or then you allow it to cool, and then crystallization will take place. So the key words there are evaporate, so heat, evaporation, and then cool and crystallization. Use full sentences, but they're the key words that you're after, right? So I'll pause it and see if you've got any questions about that. One nice exam question that I've seen which might catch you out, I mean I've just been through off the video with a few questions on this, but why would this question not be safe if you did it with a metal like sodium, potassium or lithium with, say, hydrochloric acid, nitric acid or sulfuric acid? 3, 2, 1. Boom. Boom. Yeah. Right. Okay. Required practical 2 is titration. Right. So this one, I'm not going to spend long on this because this is triple. Whoops. Triple. I can't spell the word triple. This one is triple only. And listen, folks, those of you doing trilogy don't need to know this, but what I'm going to do for about 30 seconds to a minute is remind you of a few key points, very, very briefly. So remember to use and write down all the kits you're using. So just remind yourself to look up, and again, you can have a look at it. There's some fantastic videos on this in detail on YouTube, which I've shared with you that aren't mine. So I'll encourage you to use those: pipette, burette, and talk about words like precision and accuracy. So precision, this idea that all the values will be about the same. So if values are very precise, a series of values are very precise, they'll be about the same as each other. Accuracy, in other words, they're giving the right value. Use words like swirl. Talk about the indicator, the special indicator you use. So make sure you know about phenolphthalein or methyl orange. Make sure you talk about the fact you're using a conical flask. and then talk about what the measurements you're taking, so the initial volume and the final volume to get your tighter volume. And then the fact you take rough and then multiple titrations and remove anomalies and look for concordant data, anomalies, and they love all of that stuff, right? So that's as much as I'm going to do on titration. You might have to make a salt from a titration method, that's more likely to be paper 2, or you might have to do a calculation. We'll spend a bit of time on calculations later on. All right, so that's as much, but I'm encouraging you to go away and look at it. Required practical 3, I suspect I'm not the only chemistry teacher that hasn't spent long on required practical 3. Hang on, which one's 3? Let's get that around. We'll do 3 first, then we'll do actually the one that we haven't spent much time on is 4, which is the temperature changes one, because it's quite easy, but I think it's worth spending some time on. I've got a funny feeling that's going to come up, right? So we're going to have a look at required practical 3 and 4. Required practical 3 is electrolysis. Okay, so in particular, you're looking at what's happening in electrolysis of aqueous solutions, and we've done entire sessions on electrolysis that I'd encourage you to look at. But I guess the thing I'm sending you away to think about is, can you predict the products of electrolysis? And we're going to do a little bit of practice of that now, because I really want you to be able to do this. But let's remind you of a couple of basic points though, first of all, before we start doing that. So electrolysis, you've got a couple of electrodes dipped into, so these will be made of graphite. What's special about graphite that means we use it as electrodes? It's what doesn't react and, keep going. It's made of carbon, it conducts electricity. Graphite conducts electricity, and you need to know that for the bonding topic anyway, right? So graphite, and it's also inert, it doesn't react, although for the electrolysis of aluminium oxide, remember, to produce aluminium at very high temperatures, oxygen produced at the anode will react with the carbon very slowly, and you have to replace the anode. That's that bit from this topic as well. But we use graphite in the lab, there's no issues with it reacting and so on. We've got an electrolyte here. This is a solution that's got dissolved ions in it, which I'm going to draw as little pluses and minuses. And that might be things like, I'll draw them over here, it might be sodium ions, chloride ions, and from the water you'll have a small number of hydrogen ions and hydroxide ions. These will come from the salt you've added, these will come from water, but they're all in there. Now people forget what happens in electrolysis. I've talked about this before, entire session on it, but remember that electrolysis is what happens on the surface of the electrode. The ions travel to the electrode, so the positive ones go to the negative electrode and the negative ones go to the positive electrode. So chloride and hydroxide go to the positive electrode, sodium and hydrogen go to the negative electrode, because opposite charges attract one another. Where it gets difficult, I suppose, is having to work out what products you get. Now remember first of all that it might be you're asked about electrolysis of molten ionic compounds, and that's dead easy. If there's no water there, all you're going to produce is sodium and chlorine, or lithium and bromine, or zinc and bromine. Whichever elements are, whichever ions are in the compound, they're the elements you're going to get. But if you've got sodium and hydrogen ions going to the negative electrode, you've got to decide which one of them discharges, which one of them turns into the element. And likewise, if you've got chloride and hydroxide, going to the positive electrode, you've got to decide which one discharges. So, do you know, can you remember? I want you to work through the rules yourselves for a minute. I'm going to be back in 30 seconds. You have a little chat. Then, so remember, the negative electrode, you're going to get hydrogen and sodium, or any other positive ions, whichever you've got in the pot, go to the negative electrode, and the less reactive of those gets discharged. And that's nearly always hydrogen, and so you end up with 2 hydrogen ions gaining an electron each, so 2 electrons ending up with H2. So that's what happens most of the time, and of course that's reduction because it's gain of electrons. The only time that doesn't happen is when you've got a very low reactivity metal. Really, it's going to be copper or silver potentially, and you're going to get that happening. Now, the copper ions gain electrons, but usually it's that. Now, little detail here, really pushing the level up, is if you're taking hydrogen ions out of the solution, little detail here, really high level point, you're taking hydrogen ions out of the solution, what's going to happen to the pH? If you're taking hydrogen ions away, is the pH going to go up or down of that solution? It's going to become more acidic or less acidic? Less acidic, so the pH will go up then, won't it? Right, so think about that. So for some of you just pointed straight down thinking about it, of course it's going to become less acidic, more alkaline, right? But think about the copper solution as well. We know, don't we, triple students especially, that copper ions are coloured. So copper compounds, any transition metal compounds are coloured, we learned in triple. And so if the copper ions are being turned into copper metal, which we know is copper coloured, what will happen to the colour of the solution? Tell each other? More blue, less blue, or stay the same? Yeah, the colour will fade. Yeah, colour will fade. What happens at the other electrode? So clearly where we're struggling a little bit is what happens at the positive electrode. Now remember that both the negative ions go to the positive electrode. What happens when they get there is if there's a halide, you will generate, so any halide, chloride, bromide or iodide, it will become discharged and you form the element. There's the half equation for the oxidation, right? But if it's nitrate or sulfate or just hydroxide or something else, then it's the hydroxide that's discharged. And even some of the brightest and best in the year think that hydroxide will be produced. But no, the hydroxide is discharged. And if you discharge hydroxide, you get oxygen. You'll see oxygen being produced. It will fizz. And if you can learn this equation by Monday, I'll be happy and your teachers will be happy. That's the equation for the discharge of hydroxide. And if you remember that it's oxygen produced and then remember that it's water, you can probably work it out and balance it yourselves. Now think about it. Here's the detail. If it's a reaction where hydroxide is being taken away, what's going to happen to the pH? Is it going to go up or down? It's going to go down. If it's a reaction where both hydroxide and hydrogen are going to be discharged, say in the situation where you had sodium sulfate, you'd get hydrogen ions discharged and hydroxide ions discharged. What happened to the pH then? So the same, right? Okay, good, really good. Right. Do spend some time on electrolysis. We haven't spent time in this session, although we did in the previous one on the electrolysis of aluminium oxide. That feels like a good question to look at as well. Required practical 3, I think, is brushed over somewhat potentially in class, but we shouldn't overlook it. So required practical 3 is what we call the temperature change or energy change is 1. 4. Yeah. You don't need to know the numbers, doesn't really matter. Alright. So this reaction can be done, this process can be done in a number of ways. The way that you'd have most likely done it in the lab, though not necessarily, I just ask that as a little bit more quiet when I'm trying to think, is that you do this reaction probably inside a polystyrene cup. And you do the reaction and you're stirring away with a thermometer. It might have been that you've done a reaction, say, between magnesium and copper sulfate, solid, aqueous, magnesium sulfate, aqueous, and copper, so a displacement reaction, which are always exothermic. These redox reactions like this, so magnesium is being oxidized to Mg2+, and copper ions are being reduced to metal copper. So it might have been you've done that, and you'd have to stir like crazy to make sure all the magnesium is floating, sort of mixed properly. One sec, just going to pause the video. So you might want to give that a really, really good stir. Or it might have been you did a neutralization reaction. So it might have been that you've done alkali, sodium hydroxide, being added to an acid. But there are some principles here that I want to, kind of want to press home if I can to you. Why do you do it in a polystyrene cup? You all know the answer, so tell me. Yeah, well done for spotting the deliberate mistake. 5 points to Gryffindor there. So some details of things you might be asked. The word you want for the polystyrene cup is an insulator. So if it's an exothermic or an endothermic reaction, you haven't got heat transfer to the surroundings, no heat loss usually to the surroundings. So we get an accurate reading. The thermometer, when we use the thermometer, we often stir with it to encourage mixing. But also, it's really important you measure the initial temperature and the final temperature to get the temperature change. All right, so it might be T final minus T initial, but you do, to get the temperature change, you do one take away the other. So make sure you've got all that clearly stated in your description of the practical. Why are we putting it inside a glass beaker? Well, that's to stop it tippling over. That's to stop it falling over. So we've got a glass beaker there. You might see that there's a picture from a textbook here. You might sometimes see it like that, where they've got, instead of holding the thermometer, they've held the thermometer up by stacking it inside a tripod. That's another way of doing it that can work quite nicely. So they're the general points, not difficult, but the data you get might simply be a table of data where there are a number of temperature changes you get, and it might be something like this, right? Now this is not difficult, but it's easy to lose a few marks if you're not careful. That's not the right one. Where is it? Something like, nope. Here we go. I haven't got the table I thought it had, but what I want you to be aware of is it might be you get an initial temperature and then final temperature, and then you get delta temperature. So it might, the initial temperature was say 21.0, 21.0 and 21.0 for all of them. One of them went up to 24.5, one of them went up to 24.6, and one of them went up to 30.2. Well, you can work out the temperature changes easily enough for all of them. And then this would be 9.2 or whatever it is. So remember to remove the anomalies, okay? And then work out the mean from the ones that are not anomalies. So look out for things like that. Have I done the maths right there? I haven't, have I? Probably have, whatever. You get the idea. So watch out for anomalies, remove anomalies and calculate means. You know that stuff. But the more difficult one is if you're doing one where you are adding, you start in your pot with, say, some hydrochloric acid, and you add to it a bit at a time. So let's say you've got 25 centimeters cubed of acid in there, and we add to it 5 centimeters cubed, then 10 centimeters cubed of alkali, then 15 centimeters cubed, and so on and so on and so on. And what you end up with is eventually adding enough sodium hydroxide to neutralize all of the acid. Every time you add a bit of sodium hydroxide, neutralization takes place. Neutralization is exothermic and the temperature goes up. And what you would therefore see is a graph that if you've got volume of sodium hydroxide, you'd see the temperature climbing. But the difficulty comes is what normally happens is you keep adding the sodium hydroxide until all of the acid is used up and then beyond. So what happens is eventually the temperature starts to come down again like so. And you've got to look out for that one. So the point at which that you get the maximum temperature change is the point at which those lines cross. All right, so that there is the maximum temperature change. That's your delta T. That's the value that you've worked out. So look out for that one. That's a tricky little practical that I'd like you to be able to do. And that's also the point at which the neutralization has fully taken place. So that I thought it was worth spending a bit of time on that. And what's going on here is, as you've added more hydroxide than you need, you're just adding a cold liquid to a hot liquid, and of course that'll mean it'll cool down a little bit. So where are we? The other way that I was going to mention that you could do this practical is by using a machine to do it for you, rather than using a thermometer. You could put a probe into the polystyrene cup and get a continuous measurement like so. Little extra details you can add is maybe add a lid, so that will increase the insulation and minimise the heat loss to surroundings. So that was a whistle-stop tour of the core practicals. I'll do the same thing for paper 2 at some point, and I'll give you a chance to ask me a couple of questions if you've got them, and then we'll do some quantitative stuff. So this type of question is your absolute guaranteed classic question for both trilogy and triple. So let's say you're asked to talk about this reaction. So you've got silicon dioxide reacting with magnesium. This is a good chance to remind you to make sure you know the properties of metals. Make sure you know that silicon dioxide, is giant covalent and it's got the same properties as diamond. That's always one that people forget. So silica behaves like diamond. Just remember that if you're unsure. We add magnesium to it, and this will be a reduction reaction, and we generate magnesium oxide, and we generate silicon. So it's perfectly reasonable to ask you to balance that to start with. So let's do that, shall we? So that's it then, balance, making sure we've got the same number of magnesium, silicons and oxygens on both sides, which I think I have there. And let's say the question is the exam question I've got in front of me. So you've got how many grams of magnesium are required to reduce 1.2 kilograms of silicon dioxide. So the question is, how much magnesium do you need? It might be, they say, how much magnesium oxide do you get, or how much silicon do you get? But you've got to look at, you've got to read the question really carefully. What I would do to really help yourself do this is underline the things that we care about in this practical. That's what I would do, because people often pick the wrong thing. So, as I've taught you, as you've been taught by your teachers, please get into the habit of writing down the molar ratio to start with somewhere on the page, ideally as a grid. That works nicely, 1 to 2. We're only interested in these two things, so don't bother with the right hand side. When you're writing down the mass, you must convert to grams. You can get marks for converting to grams, so don't forget those really simple things to do. Just to convert it to grams to start with, and you all know that a kilogram's 1,000 grams, and so we get a mark for turning that into grams, and that's really important. And then we've got to calculate the MR, and this is a skill that's worth a mark. The formula mass, to work out the formula mass of things, I always get people to put the thing we're interested in a box, because to remind you not to times by the coefficient there, not to times by the number 2. So the formula mass of silicon dioxide is 28, add 16, add 16, and that is 28 add 16 is 60. That's grams per mole. And the magnesium will be 24. It's just the value on the periodic table. The number of moles then, ideally you would show in the table or on your bit of paper somewhere that N is equal to the mass over the formula mass. So you might want to write that to the side, but it's 1,200 divided by 60, which is of course 20. So you're picking up marks working out the formula mass, and that you might even have picked up 3 marks by this point. In fact you do, you get 3 marks for just doing that. How easy, it's 3% of your paper on that side. Then you need to work out how many moles of magnesium you'd get. It's a 1 to 2 ratio, so you times by 2. So use this ratio up here to work out what you do to the number of moles. So it's 40 moles of magnesium. If you want to make it clear in the exam, you can say number of moles of silicon dioxide is equal to 20. Number of moles of magnesium is equal to 40. If you'd rather do that somewhere, you can do that as well. But then to work out the mass of the magnesium, we know that the mass is equal to the mR times mole. So just a rearrangement of the equation before. So you do 24 times 40, and 24 times 40 is, what's that? Help me out. You say 96, but it ain't 96, is it? 960. 960, there you go. So that's it then. Five dead simple marks, all right? Dead easy marks. Please be confident at doing these sorts of questions before Monday, because this is it's 100% guaranteed to come up in some form or another. The extra marks are usually for getting the right number of sig figs. They're also for getting the right units in grams and so on. Another question might be to work out, so for trilogy and triple, you need to be able to work percentage by mass. Percentage by mass is dead easy. Let's use the same question. So of oxygen in silicon dioxide, the way that you would do that is add up the mass of the oxygens in silicon dioxide and divide that by the formula mass. So it's 16 because there's two of them, divided by the formula mass, which was 60 times 100. So it's 32 over 60 times 100, and whatever that is, you can do that in a calculator. So the percentage by mass is a skill that's worth spending a bit of time on. And then one calculation that you need for trilogy and triple that I don't want you to overlook, it's really simple, but people forget to do it, which is the conservation of mass. So if in this reaction, for example, you've got 1200 of that and 960 of that, that's what reacts together, you can know for certain how many grams of that and that you're going to get in the end, because it will be that add that is equal to that add that. Law of conservation of mass is a required point in the syllabus. The mass of the reactants equals the mass of the products. Don't overlook the simple things. So sometimes they will say, here's the mass of the reactants, what will the mass of the products be? Or here's the mass of one of the products, what must the mass of the other product be based on the mass of the reactants? It's dead simple. It's all the same. I'll do a little bit of triple stuff now, because when I'm not going to spend time on limiting reactants. There are videos to look at on that. I don't want to spend too much time on limiting reactants, but I do want to think about the fact that you have to choose carefully which calculation to do. If you get a calculation, it's either going to be a mass calculation like we've just done, or a titration and concentration calculation, or it might be a gas calculation. The first thing you must do is work out which equation you're going to use, and that's the thing where people go wrong. It's worth remembering, if it's a titration or anything else that's got a volume and a concentration, that number of moles is equal to volume times concentration, and usually the volume's in centimeters cubed, and so we divide by 1,000. If the volume is in decimeters cubed, which is unlikely, we don't need to divide by 1,000, right? So that's the way we do that. So you can work out number of moles there. And an example of that would be a titration reaction. So let's say we've got sodium hydroxide in a titration reacting with sulfuric acid to give sodium sulfate and water. First of all, make sure you got the ratio correct, the balanced equation correct there, and so you get the right ratio of sodium hydroxide to sulfuric acid. That's really important. Don't overlook that basic mistake that often people make. Then, just as before, we write down the information we've got. No point working out the MR, because that doesn't tell us anything. Work out the volume in centimeters cubed, or if you prefer to convert to decimeters cubed and use that, you can, depending how you've been taught. Write down the concentration of whatever's given, what you need to work out, and then work out the moles. So let's assume we're told the volume of the sodium hydroxide is 25.00 from a pipette. We're told the titration leads us to having 23.20 centimeters cubed of that. We're told the concentration of the sodium hydroxide is that. Work out the moles from that times that over 1,000, which would be 2.5 times 10 to the minus 3, is that right? Yeah? Let me just check that. And then we work out the number of moles of this one by doing that divided by that. So the method's simple when you remember which skill to use. Is that maths right? Yeah, 25, there's 2.5 divided by 1,000. Yes, got to be right. And then you can work out the concentration here by doing concentration is equal to n times 1,000 divided by the volume, which is 23.2. And you can plug numbers into a calculator, right? On those states. You sure? Yeah, all right. But the message I'm giving to you is choose which equation to use first. Now, the hardest calculation overall to do, and one that you really struggled with in the mock, or when you generate a gas in the reaction, and it might be that you have to work out how much gas is left even from a reaction. But let's say you've got, I'll try and think of one to do. Let's say we've got calcium carbonate and it's being heated up. Oh no, let's react it with HCl to give calcium chloride, water and carbon dioxide. It might be that you're told the volume of this. It might be you're told the mass of that. But as with any calculation, work out the moles of everything and then you can work out the volume. And the calculation to use, the volume of any, the number of moles of a gas is equal to the volume divided by 24. If it's in decimeters cubed, you'll be told this anyway. And the number of moles is, see you later, volume in centimeters cubed divided by 24,000. Again, that calculation you'll be given. But to work out the volume of a gas, that's the one to use. And I promise the very last thing I'll do with you is one where it's only gases involved. And these questions people typically do quite badly on. So let's consider the Haber process reaction. And we'll just say that everything's, here's a gas. And I'm going to use it as a limiting reactants question as well. Okay, so this is it's a bit of a tough one. So the ratio here is 1 to 3 to 2. The volume, let's say we're told that the volume of this stuff is 40 centimeters cubed. And let's say we're told the volume of this is 150 centimeters cubed. We've got to work out the volume of ammonia in gas, the volume of ammonia we'd produce. Okay. Now that's not an easy question. You could work out the moles by dividing by 24,000, but you don't need to, because the molar volume of any gas is the same at any fixed temperature and pressure. So we know there's a 1 to 3 ratio. So the reacting volume ratio will be 1 to 3 as well. So if we've got 40 of that, how many of hydrogen would you actually use? Shout it out if you know. 120. So we'd use all of that, leaving us with none of that. We'd use 120 of that, leaving us with 30 of that. And we'd produce how much of this stuff, given it's a 1 to 2 ratio, how much ammonia would be produced? We start with 0, how much would be produced though? 80, yeah, good, plus 80. And so we'd end up with 80 of that. So the total volume would be that, add that, is equal to 110 centimeters cubed. Those sorts of questions are difficult, but that's the sort of thing that you can look up more of that sort of stuff if you need to. But I think I'll stop there. I'm going to pick out a bunch of stuff and send you spam a load of stuff to you over the weekend, and I'll do some easy things on Monday morning. Let me know if there's anything you want me to work on. Cheers.